All right, and we are live. Cool. Uh, Live control panel. No. Um, I'm just trying to set up my YouTube um, um, control panel on OBS, and okay, Google that. Google that. Google. Let's Google it. Just a moment. This is gonna give me the control panel, which okay. All right, fine. So I was trying to get a YouTube control panel for some stuff, but it appears that's not a thing for today. Okay, cool. Let me test chat is working. Hello. It seems to me like chat is working, and it seems to me like we are live. Yeah. Hide that. Hide that. Put this guy there. What's this guy? I don't know. Okay, cool. So we are on. Not gonna lie, guys. Pretty. Let me tell the guys on the group that we are on. Luffy. She likes playing with my wallet. Um, cool, amazing, cool. So I'm not gonna lie, guys. I don't know how long this stream is going. This stream is going to be. Um, Here's the thing. I'm pretty tired. Uh, it was kind of a mistake to how do I say this? It was kind of a mistake for me to schedule this stream at this point because I just had a stream and I had to go take my car somewhere to get fixed. So basically, I had to like cycle home, and I'm a bit tired because from swimming still. I'm still trying to recover. But this is not an excuse. At the very least, we're going to finish implementing the receive API. And then after we finish implementing this receive API, we can see about doing some initialization um, if necessary, if we are at that point, or we may need to do some alternate function work just to get the application to work. But when we get there, we'll figure that out. As for now, what I'm going to do is I'm going to implement SPI receive data API, and then from there on we'll read the reference document and see we need alternate function for the SPIs, and after that we can kind of move on and see we can implement a example application. Cool. So let's get this going. 1, 2, 3, 2, 3, 4. Okay. Function. First of all, let's look at the header file. Oh my word. SPI. So do we have? We do have receive data as an API. So let's go back here. Come here, just put that in, and then let's do that. Let's do some documentation. So SPI receive data. This will take SPI SPI receive data. This is the function. Receive data at param. So the first param is SPI x. This is the base address of the peripheral we are using. Then params. Then the next one I think is PTX buffer. The buffer with the data. The buffer to hold the data we receive. So this should be a PRX buffer. It's fine. RX buffer. Okay, and then lastly we need rounds len. This is the length, the number of bytes of data that we intend to receive. Okay, cool. So look, I'm going to open a couple of documents so that we can kind of go through it and get ourselves understanding. As of it, I'm gonna quickly have the thing open, chat open, so we can know if anyone says anything. So if we go to serial peripheral interface, we will find in the serial peripheral interface, excuse me, I can't talk today, we have something called a data register. The data register is data received or data to be transmitted. So basically, the RX API works just the same as the TX API. TX API, what we did is we got the data we wanted to send, and then byte by byte we loaded it into the data register as we were sending it. As you can see, the data register is 16-bit, so you can do one byte as a one byte as the 8-bit data frame, or 16 bits as the 16-bit data frame. And the data register in SPI is what we use to send and to receive data. So when we're sending data, we load data into the data register. When we're receiving data, we read data from the data register. And then I would say the firmware, the startup code and the kind of like the low level drivers do the rest for you. We basically, it will, once you do load, if we go to the block diagram, functional description of SPI, you'll see that we have an RX buffer and a TX buffer and then a shift register. So basically, when we write into the CR, SR, CR1, CR2, we should have a data register. When we write into the data register, this is moved to the shift register almost, it's like it's in the electronics. It moves it to the, as you write it, it moves it to the data register, and then Well, to the shift register, then from this shift register goes to the other device. Cool. So I'm looking. I think there is a diagram that explains this. Might be in the data sheet. Might not be here for now. Okay. Cool. So when we're reading cute animal on my desk, throw in an implementation of received data. Um, a return void um, blocking API to receive data via SPI. Okay, cool. So let's quickly. So if you can see here, we write into the data. So now the thing we're going to do is a reverse of this, where we read from the more than 0 bytes to transfer. What do we do? So let's wait for RxNE. Basically, wait for the flag that tells us that the Rx buffer. What does RxNE do? RxNE register do? That's easy. So it's here register, stated register, RxNE register. It's in the RxNE. Receive buffer not empty. What does this mean? The receive buffer just got some data. So when we get this flag, when this flag is on, that means the receive buffer can be read. SPI get status flag, PSPI X, and then this is, I think we want to SPI RxNE RxNE flag, and then we want to go like is this int 8t flag reset. Okay, stay in this while loop as long as the RxNE flag is reset. As long as the RxNE flag is reset. When it's reset, Rx is empty. So this is what makes this a blocking API. So we're waiting until something is written if into the RxNE into the Rx register, and then we'll get the RxNE flag, and then we can kind of do our thing. So PSPI, we want to do CR1, and then we want to do CR1, and then we want to do 1, and then SPI CR1 DFF. Okay, let's check. Do we have a 16-bit frame format? If we have a 16-bit, this is 16-bit. So what do we do on 16-bit? So we want to make let's make a unit 16 buffer kind of thing. PRX buffer. Okay, load 16 bits from PRX. Yeah. Okay, load 16 bits. Load the PRX buffer as a 16-bit load 16 bits into the PRX buffer. Okay, and then okay, move reader deck length. Okay, so this is len is minus 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 len minus minus minus. Okay, and then we need to int 16 t make a pointer, make and prx buffer. So basically load data into the buffer and then move the memory location forward so that the next 2 bytes are written into the. So say if you have like a 256 byte long RX buffer and then you want to read two bytes, move the address where you are writing forward by 2 bytes. That way you can keep when the next bits come in, you can handle it as that. So let's do this. PRX buffer. So this one we know, and then PSPIX, PSPI, PSPIX. DR. Okay, perfect. And then len minus minus. Okay, and then PRX buffer plus plus. Okay, move it 1 bit forward. Move the address that you're writing to 1 bit forward. This should make sense. Yeah, I'm definitely gonna do a 1 hour stream. I'm too tired. Build. I want to dock this somewhere here. Anyways, it built for now with all the problems I'm having. Clearly, I'm not very strong right now, so it's quite a bit difficult to deal with software. Funny. Next thing. Okay, so let's do a commit. I don't want it to be so huge. Just pull you in here. State dot stm cd git status git add drives git commit dash m implement SPI blocking RX API. Ooh, that's a lot of that is a lot of abbreviations. Okay, cool. I'm pretty tired. Cool. Okay, let's now jump into the. Any questions? No questions so far. Let us now jump into. I would like now to jump into the documentation of this board, the Bluepill. And what I want to check first is I want to go back to GPIO and AFIO and number one, I need to check if we need to do any alternate function coding in order to use SPI. Okay, so some SPI pins might need to be in alternate function mode in order for them to work. Or if they're not in alternate function mode, it's a different pin. So we need to go and check if those pins will work, and then we can kind of think about like doing an application. So let's quickly check general purpose and GPIO AFIOs. So let's go and look at alternate function. Alternate function and the IO debug configuration to optimize the number of peripherals available for the 64 pin or the 100 pin or the 144 pin package. It's possible to remap some alternate functions to some other pins. This is achieved by software by programming the AF remap and debug IO configuration register, which is AFIO NAPR. Okay. So in this case, the alternate functions are no longer mapped to the original assignations. OSC, OSC. So like here you see if you want to use OSC pins as GPIO pins, OSC out pins as GPIO ports PDO, PD1. Okay, that's fine. CAN2, JTAG, SWD, ADC, ADC. Can we perhaps open this? And is it possible to go to SPI1? Okay, cool. So here's the thing. I need a pen. So if we want to use SPI1, we can either use SPI1 as PA4, PA5, PA5, and PA7 as they are, or 15, 3, 4, and 5 as a remap. Okay? And then same for SPI3. It seems to me that we can directly use SPI2 It seems to me that we can use SPI2, SPI2. So SPI2, we can directly use SPI2. I want to know where the pins for SPI2 are. Pin out. Blue pill pin out. Pin out. So I want this. I want something like this. Because SPI2 does not have a remap, I'm kind of gonna focus on using SPI2. So let's look at SPI. Okay, so in case anyone doesn't understand. So SPI is purple, okay? And then when it goes like, when it goes purple, that means we are looking for SPI. And what we want to do is find out where, okay, first of all, let's look at the remap functions so that we can kind of understand. I'm slow today, which means we're going to stop this stream prematurely so I can go rest. And I might do another stream later after when I'm kind of feeling a bit strong. So let's say no remap, PA4, 5, 6, and 7. That is SPI1. Let's look at this diagram. SPI1, SPI, and then 1, which we can see here. Mozzie 1, Mozzie 2, Meso 2, Mozzie 1, Meso 1, Meso 2. That's perfect. There is an SPI3, which is A15, A15, B3, B4, B5. So A15, A15, B4, B5, this, A15, B4, B3, B4, B5, these are either SPI1 or SPI3. Okay. So this is why we need remapping. You might need to, depending on the pins that you're using and how hard you're using your application, you might need to change this. But at the moment, what we do know is SPI2 is always at PB12, PB13, PB14, PB15. Okay, so as long as we have those, we can always use SPI2, and we do not need alternate function remapping, which means we can likely we can likely do some implementation, but I don't want to start implementing yet. The reason being, is I'm tired and I kind of want to go get strong before I can come back to finish this. But in any case, what we want to do is let's go to the main file. Let's go. Let me see if we have any comments or questions. No comments, no questions. Thank you so much. Sometimes it's helpful. So let's just put in some comments here, so that we know what to do when we come back in. Okay, so let's do this. Initialize GPIO pins for SPI. So output mode, no PUPD, fast speed. Okay. Fast speed. No alternate function mode at the moment for SPI2. No alt FN for. Let's actually just quickly do something here. Okay. SPI2 doesn't need a file remap. I think so. Let's look at remaps. There's nothing. There's no remapping that's needed there. So it's gonna be what are the pins? PB15 as Moshi. Am I wrong? SCK NSS 13 and 12 SCK NSS. Okay, so let's do void SPI. Let's initialize the pins we need. Okay, SPI GPIO init. So the pins we need, let's initialize the pins we need so that we can, like, we need to start those pins so that we can use them to run SPI. Basically, number one, get that port on, get that port on, start the B port, set these pins as the output, and the comments that we did to this. Basically, start the B port, put them in output mode, remove no pull up, no pull up, fast speed. Once we set these pins, we can kind of start from there. Okay, cool. So GPIO hello team SPI pins. Okay, SPI pins dot GPIX is equal to GPIB. Okay, so we want to use port B, SPI pins, dot GPIO pin config dot pin mode. GPIO mode out, open drain, no PP. Okay, and then we need SPI pins dot GPIO pin config dot pin direction equals to GPIO dir out fast. Cool. That's really it. We don't need to set. We have set the pin mode. We've set the pin number just now. We have set the direction out fast and no PD. Cool. So let's set up the MOSI and MOSI. Okay. SPI pins dot GPIO config dot GPIO pin number we'll get to output type later. Okay, pin number PB GPIO pin no 15. Okay. GPIO init and SPI pins. Okay, cool. So now we just go down the list and do this for the other four. Okay, so this is 14. SCK, this is 13. NSS, NSS, this is 12. Okay, okay, cool. So this is the beginnings of the application. So now what we have all the pins for SPI2. We have all the pins for SPI2 initialized as the GPI, the kind of GPIO pin you want. So it's a output mode pin, no pull up, no, it's an open drain pin, and then it's a fast speed pin. Okay, and we don't need to do alternate function for SPI2. Okay, to get SPI2 going. So okay, so let's initialize SPI2. Void SPI2 to init. So now we initialize the peripheral itself. Okay. Wait. Where do you want to go? Okay, so now let's. I'm just gonna quickly check for questions. No questions. Let us now initialize the SPI2 peripheral itself. Okay. So SPI handle T, SPI2 handle. So now this is SPI. We're gonna do SPI handle dot pspix equals to SPI2. Cool. And then let's do bus config SPI handle dot pspix dot. No, this is config dot. Let's do a bus config equals to, let's set this as FD. SPI FD SPI bus. This is a full duplex. Okay. SPI2 handle dot SPI config. So dot SPI device mode. We're going to set this as a slave. SPI device SPI device mode slave, and then SPI2 handle dot SPI config dot clock speed is equals to SPI CLK. I'll use 4. Okay, SPI handle dot SPI config dot SPI DFF equals SPI DFF 8 bits 8 bits. Okay, cool. And then SPI handle dot SPI config dot okay, dot SPI config DFF. This is now CPON equals CPON low handle dot SPI config dot SPI CPON C phase. So let's go with low and then SPI handle dot SPI config. Let's choose hardware SPI SSM disable. So let's choose hardware slave management. SPI init. I can see the code is built properly. My issue is for some reason I cannot zoom in that panel. I can't zoom in, but I can't see the code. If anyone knows how to set up Eclipse so that we have a custom font size all over, please let me know. This would be really helpful. What else? Okay, cool. So now we've implemented initialization of SPI and we've implemented the buttons that we need. So, SSOE. We do need to deal with SSOE, which I'm probably going to deal with offline. SSOE. Did we build an SSOE API? I wonder if it's SSI, so that way, we don't need SSOE because this SPI, we need the enable. Cool. Okay, cool. So basically what we need to do now is start sending the data. I need to connect my hardware, and then I need to. My cat is falling. You really have to figure out somewhere to sleep. That's not my desk. Okay. Okay, cool. So seems like this was a good stream actually in the end. Um, we got an sample application here going. We basically initialize SSI and SPI. Um, we can actually quite quickly confirm all of this. So I will try and run debugger's STM32 application. Actually, stop. Sorry. In main, we need to call I'm thinking. Inside of main, we need to call that's fine. Inside of main here, we need to go, okay, let's fix it. So init SSI SPI2. Okay. So first of all, SPI2 GPIO. I would have called it something different. Okay. SPI2 init. Init. And then SPI SSI configuration PSPIX SPI2, and then let's enable. Okay, so okay, cool. So what I'm going to do here is I'm going to run this application, debug this application, debug as STM32. That looks successful. We should go into the debug console just now. Oh, I cannot see why. I don't know why it's timing out. And I need to make this console bigger by itself. Um, um, that's fine, I'll copy that. Let's copy that. Let's minimize here. And then let's go just here. Just go here. For now, let's just put in ST transfer dying out. Now device found on target. Cool. Now let's just quickly disconnect and connect. And then let's try it again. We should know it's working because it should put us in the debug perspective. So debug as STM32 configuration. remove my F4. My F4 is also connected. So I'm going to just quickly make sure all these wires are clearly connected, because my application keeps failing because for some reason it keeps thinking my device isn't hooked up. Actually, quite funny. You can use the debugger on the F4. Like you can use the ST link on this one to actually. Oh yeah, I see why. I see why. My ST link terminals are really weak. So it's the USB. I need to go and get a new um, ST link. I should be able to do later today. I probably have one lying around, but let's see. This seems to be a device. Debuggers. Let's see. Debuggers. Boom. So we are now in the debug perspective. So I think I'll go to SFRs, and then number one, let's just, we have not run GPIO in it or whatever. So number one, the first thing I want to do is check before we run the code, so that we can actually confirm that it's working. So I want to go in RCC. I want to go into the RCC struct, and then I want to do. I want to find. I think it's APB2 SPI. Is there SPI in here? FIO, SPI1. No. So I want to go into APB1, and then I'll go look at. Don't do that. 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 Please don't do that. As you can see here, SPI2 is not enabled, but we're still in the first line. So let's kind of walk through until past. So let's go GPIO inits. If we enable, so IOB, IOP, IO port A, IO port B, not enabled. So if we run GPIO init here, we should get GPIO2 enabled. Cool. IO port B. Perfect. IO port B is enabled. Okay, cool. Now, if we run SPI2, no. Hey, come on, go. If we run the okay, let's look at APB1 ENR, and we see SPI2 is still off. So if we run SPI2 initialize, we should have SPI2 enabled here. Okay, let's do it. Cool, SPI2 is enabled. Perfect. So now, actually what we want to go do is we want to go look at the SPI2 peripheral itself and see what we can learn in there. So I have a culprit here. Let's look at CR1. Bi-di mode off. Bidirectional mode off. Okay, cool. DFF1. What does DFF1 mean? So let's look at SPI registers. SPI CR1. DFF1 is 16-bit data frame. So that's not good. DFF says 1. That's not good. Software slave management says SSM 1. Software slave. Okay. SSI, internal slave select. It's also 1. Cool. And then baud rate and CPOL and CPA, that's 1. So, okay, so there is a problem here. This is low, this is disabled, and this is 8 bits. And these are not being handled. Let's perhaps see if we can handle those, because this code is not doing the thing we want. So data frame format should be 8 bits, should be 1. Okay, cool. So let's go look at why is the data frame format being the wrong format. So now basically we are just testing this code by walking through the registers and the manual to find out why. 8 bits, okay, DFF 8 bits. Cool. So let's go to the SPIC. We want to go to the initialize device mode master. We never checked that. Okay. Bi-di mode, die mode, and full duplex cool. This is also bi-di clear. Okay, cool. Configure speed using baud rate, that's fine. Configure frame size. So let's look at the CR1 DFF. Okay, so I want to go to SPIH and I want to see what does 8 bits mean. 8 bits is 0, 16 bits is 1. So why does no okay right. So why does the frame size and the SSM oh, which code did we run? Yeah, this is the one we run. Let's run this again. Step into Step into. Step into. Okay. SPI handle peak clock control. Enable SSI. That's cool. That's fine. Okay, cool. Okay, now this is just not constructing stuff, constructing stuff, constructing stuff, constructing. Okay, cool. BiDi mode cleared. BiDi CRC not enabled. BFF 1. I don't like that. SSM 1, SSI 1, LSB fast 1, SPE 0 because it's not enabled yet. ER 1, master 0, cool. CPOL 1, C phase 1. SPE will be enabled after this. Yeah, you see SPE here will be enabled after this. This is not even nice. SPE was never enabled. So we have some issues. We have some issues. Number one, the master stuff is going well. The CPOL and C phase is not going well. And then we also have LSB fast is not going well. The reason being the reason is LSB fast is not going well is because we never actually set it. SPI handle .SPI config .LSB fast equals SPI let's forget this one first. Let's be fast. My issue is master is slave. That's fine. CPOL is low, and C phase is low. But those are 1-1. Why? And SPE is never enabled. Okay, cool. So I'm gonna stop there and kind of debug this code, and then I'll come back to you guys when I've figured out what is wrong. I'm gonna check if we have any questions. No questions at the moment. So thank you. Thank you all so much for attending today's stream. That was amazing. And yeah, cheers. I'm gonna stop there to now. The objective now is to go and debug why my setup isn't working. Why am I getting the wrong CPOL, C phase, and the wrong CPOL, the wrong C phase, and why is it SPE being enabled? So I'm gonna figure those out, and then I'll come back.